So, welcome all of you to Basecamp 8 session 2. Today the topic is going to be deep dive. We're going to go deeper into architecture, for example, and other interesting topics about Starknet. So, as you know, we have 4 sessions for this Basecamp. This is session 2. Next week, Cairo is going to be more hands-on, more programming. Today is going to be more about theory, still similar to last time. Topics covered today, we're going to talk about transactions on a Starknet, data availability. This is some of the topics about what makes a layer 2 a rollup. We're going to talk about the 2 different types of finality that you find on Starknet. And then I think the break's going to come after full nodes. Then recursive proving is going to be pretty much the main topic of the session. Okay, first topic today, transactions. And we saw a little bit of this last time as well in session 1. All right, so just to summarize where we left off last time, we talked about the architecture and the flow of the transaction. It all starts with your smartphone or your laptop that has a smart wallet. And obviously, the smart wallet is the one who signs transactions and sends it to the sequencer. And in this case, arrives to the mempool in the sequencer. And in the mempool, what we do is just a very light transaction validation. For example, that the structure is correct with the transaction. Obviously, then, which I'm not showing here, we do like a signature verifications, but that doesn't happen in the mempool. The mempool is more like a more basic validation. But at some point, the transaction is executed in the Cairo virtual machine. And that execution creates what's called an execution trace, which is sent to the prover in Sharp, which is one of the services that created by Starkware to serve Starknet and StarkX to create validity proof for both. And then the validity proof is sent to Ethereum to a layer 1 smart contract known as the verifier. It's a Solidity smart contract to attest to the integrity of the computation of the transaction, right? So this is what we discussed last time. And also, as part of the output of the prover, you don't not only get the validity proof, you also get the result of the computation. This goes to the very first example that we had about the space exploration problem. Now, let's actually think about the different statuses that the transaction actually goes through as it navigates all this life cycle and touches all these systems. So on the right-hand side, just take a look at the transaction status and you see how it changes how the transaction actually moves in the system. So when the transaction actually arrives to the sequencer, the first status that it gets is received. If it's received, it just means that it arrives to the mempool and actually it conforms to some basic verification of the transaction, mostly that the structure of the transaction is correct. If that is not even the case, that it's like a wrong structure, then the transaction just gets ignored. Ignore is not a status. It's just so you know that it's not going to be even considered by the sequencer to be executed. The first real state will be received. Then, obviously, as I mentioned, the mempool does a very basic validation of the transaction. At some point, a more strict verification of the signature is performed, signature of the transaction. That happens in the sequencer. So if that signature is verified successfully, then your transaction continues in the process. There's no change in the status. It continues being received. But if the transaction actually has an incorrect signature, it will change to the status rejected. And that will be the end of the cycle of that transaction in particular. But if the signature is correct, then it moves on to the next status, which is basically going and execute it in the Cairo virtual machine. And if the transaction is executed correctly, then the next status that it gets is accepted on layer 2, on L2, as you see on the right-hand side. But if, for example, the execution fails because maybe you didn't have enough gas to pay for it, or you hit an assert in the execution and that assert turned out to be false, then the transaction is stopped and then marked as reverted. So a reverted transaction basically doesn't modify the state of Starknet, but it still gets included in a block and you still get charged for gas fees up until the point the transaction actually failed. So 2 options, either accepting a layer 2 or reverted. And those are real statuses that you will see on a block explorer. Then obviously it goes to the prover, the trace, and from the prover, you create a validity proof, send to L1. And if that validity proof comes to be verified successfully, then the last status that transaction will get is accepted on L1. So as you can see, a successful transaction goes through the following states: received, accepted on L2, and accepted on L1. There are two ways that it can fail, basically incorrect signature, or simply the transaction was reverted because it hit an assert, or it didn't have enough gas for the execution. If you go to a block explorer, you will see this status all over the place. Yeah, Omar?
So in that scenario, what is the role of the nodes?
The nodes, the full nodes,
Yes, the full nodes. Yeah.
we're going to see that in a different section.
Oh, okay.
Yeah, today. But just to show you a simple transaction, let's just pick one transaction random here from the block explorer. And you see here, for example, obviously the very beginning is not received because it's just being sent. Eventually, when it hits the sequencer and it's acknowledged, it gets to received. Pending, accepted on L2, and then accepted on L1. This pending, I guess, is just waiting for the mempool to be executed. But the real finality, let's say, will be accepted on L2 for layer 2, and the finality for L1 will be accepted on L1. Question for Douglas URL. Will the L2 rollback in the case of L1 rejecting the proof? So in that case, you will have a big reorg. But yeah, it could be painful because it will be a reorg of basically 2 hours of blocks being produced. All right, so there are different transaction types that you can send to Starknet. The first one that we actually saw last time is the declare transaction, where basically you register new code in Starknet. Whenever there's a new smart contract that didn't exist before, you have to declare it on the Starknet, and you have a specific transaction for that purpose. One thing to clarify is that a contract that has been already declared, if you plan to use it as well, you don't have to redeclare it, right? If you try, the transaction would fail just saying, hey, this has been declared already, you don't have to pay for it twice. Which means that, for example, for an ERC20 token, much likely someone already declared the ERC20 code, and then you can just deploy your own instance without having to redeclare that code. It exists already on the Starknet. Next, you have the invoke transaction, which is the one that you most commonly will use, and basically to interact with functions of a smart contract that modify the internal state of a smart contract, right? Or modify the global state of Starknet. Yeah, Omar?
Yeah. Where do we need to declare? In the sense that, is it cheaper to not having to deploy every time and to manage declares, or what is the advantage of using declarations?
The advantage is that otherwise you will have to declare the same code over and over every time you deploy. Imagine how many ERC20 tokens are out there, maybe hundreds or thousands. Like if you didn't have that declaration step, each deployment of those tokens will repeat the same code, bloating the network states, right? While when you have declared, you only upload the code once, and then you only create instances of the same code, just assigning new, storage slots for and defining things like, for example, the name of the token, the symbol, but
In the
you
constructor.
have less overhead in the global state of the network.
Okay, thanks.
So invoke is what you will use more. And there's a third type of transaction called the deploy account. And that one is used for a very particular use case, which is to deploy account contracts, right? Which is associated with the smart wallets. We saw a little bit of this last time as well, the role of an account contract. And basically, just to summarize that, an account contract is just a smart contract that has a very particular interface, the SNP6, and it's used in conjunction with your signer, right? So when you have a smart wallet, you will have a signer in an account contract, which is a smart contract on a Starknet with a particular interface that belongs to you and holds the asset for you. So all these transactions, declare, invoke, and deploy account, they all modify the global state, right? Maybe they modify the state of a smart contract, but by doing so, they also modify the global state. And for that reason, you will have to pay gas fees, right, to execute them. Now, if you only want to read from a Starknet, for example, there are some functions of a smart contract that they don't modify the state. They only give you back some data or read from state or have some logic. You can actually interact with those functions without using a transaction because you're not modifying the state. So that's like a real only operation that you don't have to pay gas fees. And as you're going to see later today, that's one of the roles of a full node, right? To try to provide that data for you without having to even touch the sequencer for that purpose. One thing that seems to be missing is like, how come there's no regular deploy transaction? Why there's only deploy account for account contract? And again, we talked about this last time. When you want to deploy a smart contract, one that is not an account contract, just a regular one, you actually use an invoke transaction, and then you talk to what's called the universal deployer. And that universal deployer is the one that actually does the deployment for you using a specific syscall called deploy. But it's not a transaction. It's just a public good on a Starknet that deploys every single smart contract on the network. Question for Douglas. What does the gas fee encompass? Prover execution plus the L1 fees? I believe right now is only the fees of layer 1, if I'm not mistaken. You have any other knowledge of this, or?
No, but maybe we pay for the Star Wars sequencer or not.
I don't think, not yet. It's mostly the layer 1 cost being spread out. Eventually, it will be also cost of layer 2. For example, the service of sequencer and the service of the prover. But for now, it's as layer 1. And we're going to see exactly.
No, so just to say that, by the way, the transaction cost has been decreasing a lot since the last upgrade. I think like 30% since the last standard upgrade. So that's great.
Yeah, the way it was reduced is that now the metering of the transaction is done more with more, let's say, more detail, more fine-grained detail. But yeah, it was a big decrease of the cost. Counterfactual deployment. So let me try to explain what the issue is here. So when you want to create a smart wallet, you have to deploy the associated account contract, right? Which is a smart contract. But to deploy an account contract, you have to pay gas fees, right? Like any operation. But to pay for gas fees, you need a smart wallet. Pay for it. So you get into this chicken and the egg situation, right? To deploy an account contract, you need an account contract, which is like a circular dependency. And the way to get out of this circular dependency is by doing the counterfactual deployment. And the way that it works is basically you first calculate the address of your smart contract off-chain, because that address is deterministic, it's just based on the code and mostly on the code itself. And things like the arguments being passed to the constructor. You can find in the docs exactly how it is calculated. The thing is deterministic. You can actually, when you use something like a Starknet, a CLI for a Starknet, you can say, okay, this is going to be the address, even if it's not deployed yet. Then you will send funds to that address. In this case, you will have to send Ether because that's what we use to pay for gas. Even though at this point, there's nothing being deployed in that address, right? It's just like an empty address. But you know that when you deploy, that's where your smart contract is going to be deployed to. And at that point, that's when you actually use the deploy account transaction to deploy your account contract. And the sequencer will know that when you use this particular type of transaction, it will not try to deduct the gas fees from an account contract. It will actually deduct the fees for deployment from the Ethereum or the Ether and that address that you pre-calculated, right? So that way you can actually deploy your account contract without having another account contract to pay for gas fees. It's a different process that follows the sequencer for this purpose. So to summarize this section about transactions, there are 3 types of transactions. You have declare, invoke, deploy account. And then the life cycle of a successful transaction will be received, accept on L2, accept on L1. And if it fails, it will be either rejected or reverted. And to deploy an account contract, you use a different deploy process that's called the counterfactual deployment that uses the deploy account. Let's talk about now about data availability. And this is a big topic on Twitter. Anytime something brings up if a layer 2 is a rollup or not. So let's talk about the liveness problem. You know that on a Starknet, as in pretty much any other network, you go from certain state N to a state N plus 1 just by executing a bunch of transactions in a block, right? In the case of a Starknet, you actually do it through the Cairo. Now, to know what is the current state of the network, right, that state N, you can either talk to the sequencer knows what's the current state, has all the details, or you can talk to a layer 2 full node, a Starknet full node, which we have 3 different clients for that. We have Juno, Papyrus, and Pathfinder. Those are clients that run on your computer. So, you know, there's a single sequencer, but there are multiple layer 2 full nodes, so you can get that answer from either one of them. But the question is, what happens if for some reason the sequencer and all the full nodes stop responding to your request, right? Like they get destroyed and there's no choice about the state of the network. If that ever happens, which is very unlikely, then the network will get stuck. right? You will know the transaction will be able to be received, but you cannot move to the state n+1 because you wouldn't know what state n is. So the network is stuck. Now, the way that Starknet is solving that, which is similar to other layer 2s, is that after the validity proof is sent to layer 1 to the verifier, we also send what's called the state diff. Basically, what the changes on the layer 2 state from the last time we sent a validity proof to this time. And this is big, right? This is a big amount of data that we send as call data. We don't directly store it, just send it as call data. And it requires a lot of transactions to actually send that data over to layer 1. If we take a look at this smart contract, it's called the memory pages. You can see, for example, all these transactions belong to the same validity proof. And there could be, I think, like 150 transactions or so. All of this is this the same. A single validity proof has all these transactions just to post the state changes of Starknet to Ethereum. It's still same validity proof, still. It's like a lot of transactions. You will see when is the pre-validity proof because there's going to be a jump in the time. Anyway, here. So this is the beginning of the first or the last transaction of data availability for the previous validity proof. So that has some implications, like the fact that we do this. So first, that we basically do this so we can recreate the state of a Starknet from layer 1 in the unlikely case that the sequencer and the layer 2 full nodes actually explode and disappear. So obviously Starknet at some point it started with an empty state and it had a genesis block and then multiple blocks after that. At some point we sent a validity proof to attest to the computation of all these blocks, and after that we send the state difference, right, from the empty state to whatever changed as a result of executing all these transactions on all these blocks, and it's sent to L1. Obviously, more blocks on layer 2 are produced, and then sometime after, we send another validity proof for this node and a new set of transactions for data availability, the new state difference. So you can see that if you take all these things that are sent to L1, all these state changes, you can actually reconstruct the layer 2 state just by pretty much applying the state difference on top of another one in order. And that's the role of a layer 1 indexer, right? So now that if a Starknet actually disappears tomorrow, you will be able to recreate the current state of the network just by indexing data from layer 1. Douglas is asking, when I exit layer 2 to layer 1, does the bridge contract check the memory pages to see what my balance is? That is done through messages. There's a mechanism to send messages back and forth between layer 1 and layer 2, which I'm actually not covering in Basecamp, but you can check it out how it works in the Starknet docs.
Which is something very interesting because this is practically self-custody in practice, right? And you can also achieve it in the StarkX. For example, when you're using DYDX or Sorare or Immutable X, you can also exit at any moment you want. So you can exit your resources into the layer 1. There's a special contract in the layer 1 that calculates the balance and then allow you to make a escape using escape hash, which is the mechanism in the case of StarkX. You can withdraw your resources. So this is amazing because it's self-custody for particular cases such as futures trading in the case of DYDX, NFTs in Immutable, and so on. But this is very, very, very interesting topic. And it was recently announced in DevConnect that the Starware team is working in escape hatch mechanism for Starknet. So that would be very, very cool.
Yeah. So just to make clear, the escape hatch exists today for StarkX apps, not yet for Starknet. It's being worked on. The idea is that if you get censored by the sequencer, you can still exit the system with your assets to layer 1. So what exactly do we send as data availability to layer 1? Right? I mentioned that the state diff, but how does it look like in practice? So imagine we have 3 people here, like a Jimmy, Rose, and Nick. Okay. So imagine that Jimmy sends 1 ETH to Rose, and then Rose sends half an ETH to Nick. So what we send as data availability, let's say these are all the transactions that are part of a single validity proof, it will be the changes, right? Not the new balance, just the changes. So in this case, Jimmy has 1 less ETH, Rose has half an ETH more, and Nick has half an ETH more. So that is what's sent to layer 1 to the memory pages smart contract. Other example, let's say same beginning, Jimmy sends 1 ETH to Rose, and then Rose sends 2 ETH back to Jimmy, and then Jimmy sends half an ETH. You see that we have 3 transactions, but what we send as data availability is only the changes as a result of executing all these transactions, which is that Jimmy has half an ETH more and Rose has half an ETH less. So you can see that even though we have more transactions, in this case, we send less data to layer 1. So these transactions in theory will be cheaper than in the first example. The more extreme case will be when there's no changes to the state when you execute all the transactions. For example, if Rose sends 1 ETH to Nick and then Nick sends it back, then nothing is changed and nothing is sent as data availability layer 1. So that will be the cheapest transaction you can find. And this is a common or well-known trick on a Starknet for different projects that actually want to have reduce the cost of their transactions to the minimum. And this is important because paying for this data availability, as you saw, that is so many transactions that we have to send to Ethereum as cold data, is actually 90% of the cost of a layer 2 transaction. So anything that you can do to reduce the amount of data it's sent to as data availability to layer 1 actually has a direct impact of the cost of your transaction. Now, how can we reduce this data availability cost? There are 2 main mechanisms. One of this is to actually wait and implement EIP 4844, and the other one is to implement volition. So in the same approach, in the first one with EIP 4844, what happens is that we will be able to send data availability info to layer 1 as blobs instead of cold data. And the benefit is that type of mechanism to posting data to Ethereum will be, in theory, cheaper than the regular path that we use today. So that will make layer 2 transaction cheaper. The downside is that that data that you post as a blob has a lifespan of only 1 month. After that, layer 1 nodes actually prune that data, so they disappear from Ethereum. We expect this to be implemented by at some point tops mid this year on Starknet, because we're waiting for the Ethereum to actually first implement that on Ethereum mainnets, so we can actually take advantage of that. But as soon as that is enabled, the Starknet will try to implement the same feature to actually take advantage of this. Obviously, this not only benefits Starknet, it benefits all the rollups, because all rollups use Ethereum as a data availability layer. You will be using this type of blobs for DA. Now, but volition is different. Volition, the idea is that you can basically choose where to store data or the data for liveness for use. You can say, okay, I want this to post it to Ethereum, or I want it to be posted off-chain. And off-chain could mean a data availability committee, could be, I don't know, a system like Celestia or EigenDA or whatever. So you have the option like either on Ethereum or something else. And you pay different fee based on which option you actually select. The idea is that will be cheaper than using EIP 4844. We don't know exactly when that's going to be enabled on the Starknet. The only thing for certain is that it's going to happen after EIP 4844 is supported. And of course, this only benefits Starknet. But I know that other projects are trying to implement something similar, just with different names. Question, will the token contract, etc., needs to be upgraded when Volition goes live? I don't know yet, because there hasn't been a design that I'm aware of how it's going to work. We're going to have to wait a little bit longer for the Starknet team to tell us how they plan to actually implement it in the system. On average, do you know how often are we sending proofs and data to Ethereum? Is it whatever happens first, certain number of blocks, certain amount of time? 2 to 3 hours, we send a validity proof to layer 1. And then after that, it's accepted or verified. That's when we send DA data to Ethereum as well. So those 2 things are connected, just happen in that order. I'm going to talk more about how Sharp and the prover works later today. So maybe that's going to help to clarify how that works, like the thing that we wait until a certain time. So far, I've been talking about the prover, interacting directly with the verifier layer 1, but it's not really the case, right? The prover, it only cares about proving an execution of a Cairo program. It doesn't care about really Ethereum directly. That's why there's another module within Sharp that is actually in charge of being the interface between Sharp and Ethereum. And internally, it has an externally owned account for Ethereum, right, to send transactions. So that is the actual module that sends the validity proof and the state diff to the memory pages. So the output of the prover goes to the blockchain writer, And that's the ones who actually interact with Ethereum to send data to the correct location. Douglas is saying, Starknet tech stack is bulletproof, really. After receiving a bunch of centralized garbage for years, I'm quite excited. Yeah, you can see how interesting this technology is and how powerful it can be on a Starknet and even apply on its own in different scenarios. So I want to show you the blockchain writer because when you go, for example, to the memory pages that I have open here, by the way, you should be able to see who is sending. Okay, let me open one transaction. This is from the memory pages smart contract. And you can see that it's coming from the Sharp blockchain writer, right? So this is the EOA that exists within Sharp that is in charge of all these transactions. And you can see that it has a lot of money. So Sharp doesn't run out of money to pay for gas fees on layer one. And it's a lot of money that Sharp pays to Ethereum for DA in particular. Okay. So one thing that I haven't discussed so far is it's called the Starknet OS. And the Starknet OS is basically to answer the question, like why is the state diff the output of the prover, right? Why in particular the state diff? And that is because the Starknet OS. The Starknet OS is a Cairo 0 program. So Cairo 0 is the older version of the Cairo programming language, not the one that you're used today. So that program has actually 4 different inputs. One input is the current state of the network. The second input is the new blocks that have been created since the last time a validity proof was sent to layer 1. So this accounts for transactions coming from declare account transaction and the invoke transaction. And then the class hash and the compiled class hash as a result of the declared transactions, right? That's what we discussed last time. Let me finish this slide and I go back to your question because I know I have some questions. Now, the output of the Starknet OS program will be the state diff, right? Takes the current state, execute the transactions, the new transactions and the new blocks. You see what changes in the state. And then it just passes as an output the class hashes and the compiled class hashes of new code being declared on layer 2, right? So the output of the Starknet OS is those three variables, let's say, state diff, class hashes, and compiled class hashes of newly deployed smart contracts. Now, the Starknet OS sits here, right? So the sequencer executes a lot of transactions, create a lot of blocks, and eventually there are enough blocks to actually trigger the creation of a validity proof. So that's when actually all these blocks are passed to the Starknet OS to calculate the state diff and these 2 things, class hashes. And that is the program that's actually being asked the prover to prove, okay? So that is why the output of the blockchain writer, this output, is those 3 things. And those 3 things is actually what goes to the memory pages smart contract. This is why the prover itself is the one that is open source, right? The Stone prover is actually written in Cairo 0 or is for Cairo 0 programs and not for modern Cairo. It is because right now the Starknet OS is also written in Cairo 0. So that's what it's been needed right now to create the data availability information. If you follow this link, you're going to see the GitHub repo of the Stone prover. This is an open source project. Basically, is a prover being used instead of Sharp. But keep in mind, this is for Cairo 0 programs because the Starknet OS is in Cairo 0. Eventually, I imagine that will be migrated to Cairo and there will be a new version of the Stone prover supporting modern Cairo. Questions from Jordan. It's asking, is Sharp payment for DA subsidized or is it one-to-one with fees paid by the users? I believe it's just paid. I don't think there's any subsidy. This is one reason why Starknet is not the cheapest layer 2 as well, right? If you go to L2 fees, we can compare the fees of different layer 2s. You can see the Starknet is not at the top, it's not the cheapest, it's not the most expensive, it's somewhere in the middle. If you actually analyze all the transactions that we sent for DA, basically all the transactions coming from the blockchain writer, you're going to see that Sharp is paying millions of dollars for block space on Ethereum every month. Please, if you have questions, put it in the Q&A section. Now some people have their hands raised. Okay. Question from Douglas. How is it more expensive than optimistic rollup? I think they need to send the whole raw data instead of the state diffs. I think they do, but they have compression, which we haven't enabled yet. That's one optimization that we're working on as well. to implement compression on DA. Right now, it's not compressed at all. So let's talk about data availability modes, there are three. At least right now, there are really just two, but a third one coming later. So we have the rollup mode, the validity mode, and the evolution mode, right? So different layer twos will have different DA mode. So in the case of rollup, what makes a layer two a rollup is that the data for DA is actually is posted on Ethereum. It's not posted on Celestia, it's not posted to EigenLayer, because if they do that, automatically there will not be a rollup. Now, the benefit is that you will get better liveness, at least compared to, I don't know, sending the data off chain to some strange service. I'm not saying that Celestia or EigenLayer are not good, but we know that Ethereum has a very good track record. So it gives you a very good liveness guarantees, but it's more expensive, way more expensive. Maybe going to be a little bit cheaper later with EIP 4844, but there are other trade-offs there involved as well. Now, Starknet, because as I mentioned, we send data to the memory pages, smart contract, it is a rollup. Now, the case of Validium, these are layer twos that don't use Ethereum for data availability. So you get worse liveness guarantees, but it's cheaper. Transactions on Validiums are usually way cheaper than on rollups. And we know that because StarkX is a Validium, and transactions on Starknet are super cheap. Finally, the third DA mode is called Volition, which is a hybrid DA mode. It's a mix between rollup and Validium because the user is able to choose where to store the data, right? Is it on-chain or is it off-chain? And that's something that's going to come soon to Starknet, maybe this year, maybe beginning of next year. I don't know exactly when. How does pruning of blob data impact data availability? Does this mean that when a block is pruned, that means the data is no longer available? That's a great question. That's a trade-off I was talking about, right? Like with a blob is only available for 1 month. So what happens when that month elapses? That data is going to get pruned. It's going to disappear. We're going to have lower liveness guarantees as the current situation. But the current situation is also not the greatest because cold data, there's no guarantee that cold data is maintained by all the nodes all the time, right? Some nodes, they may not care about preserving cold data that happens, I don't know, a year before. So there's nothing in the let's say, the protocol that say that cold data has to be available all the time for the full length of the Ethereum network. But it's more or less the case. It's yet to be seen what's going to happen with EIP 4844, lower guarantees. But the idea is that probably there's going to be some services that's going to actually store the data for longer and make it available, maybe similar to what you have like a bigger service that provides the data. I don't know. That's something that all the rollups are actually studying and looking closely to see what's going to be the impact. The benefit or the good thing is that by that point in time, Starknet is going to have way more layer 2 full nodes available, right? And probably we also going to start working on decentralizing the sequencer layer. So the probability of losing the layer 2 state is going to be lower as time goes by and as the network gets more decentralized. Jordan is asking, if a StarkX is a Validium, where does the DA live for current StarkX apps like DYDX? They go to what's called a data availability committee, basically big players that have replicas of that data. I don't know for certain because I don't go deeper into StarkX, but you can check the docs to see exactly who is this committee, right? Which companies are part of that. But it's not Ethereum, that's for sure. Now, in summary, for DA, so data availability prevents Starknet from getting stuck, which is this is the liveness guarantee or the live. The Starknet sends state diffs, class hashes, and compiled class hashes as data availability. These are the outputs of the Starknet OS program. In subsequent diagrams, I'm going to keep saying state diffs as DA, but you know that it's not just that. It's also class hashes and compiled class hashes of newly declared objects. This data is sent to layer 1 to a specific Solidity smart contract called memory pages that I showed you. That is a bunch of transactions. And because a lot of transactions is actually 90% of the cost of a layer 2 transaction comes from the cost of paying Ethereum. EIP 4844 and Volition will reduce the cost of DA and therefore the cost of a layer 2 transaction. And Starknet currently works in rollup mode. In the future, is expected to offer Volition mode. You get to choose between rollup or Validium. Let's talk about Finality. last week, actually, I showed you this slide saying that on the Starknet, you get layer 1 finality roughly every 2 hours. That's when we settle validity proofs on layer 1. But then layer 2 finality actually happens much faster, about 3 seconds. So I want to show you the difference between these two levels of finality and when do we consider a transaction to be final. So we have seen this diagram many times before, right? The whole workflow. So the idea, like if you're the user waiting for a transaction to be final, when does that happen? So layer 2 finality happens as soon as your transaction is executed by the Cairo VM. And that happens pretty much as soon as the mempool says that your transaction, it's okay, like doesn't have any issues, and it gets executed. So that happens very fast, like about 3 seconds from the moment you send a transaction. Now, finality on layer 1 is actually takes longer because then you have to wait for the validity proof to be verified on layer 1. And that happens roughly 2 to 3 hours, right? So see that's where they come from, right? Layer 2 finality and layer 1 finality. Now, layer 2 finality, there's some trade-off, right? If you're gonna take that as a final, then you're basically trusting the Starkware, right? Because Starkware is the one who manages the sequencer, basically the sequencer, right? Your third is not cheating, but it is the finality most used by apps on a Starknet because it's very fast. But then layer 1 finality takes longer, but the benefit is that it's completely trustless, and you don't have to trust Starkware, you don't have to trust anyone. If the validity proofs is verified correctly, it's guaranteed that the action was correct. And it's what's being used mostly by bridges. When you want to move assets from layer 2 to layer 1, you have to wait that amount of time. Although there are services that for a fee, you actually can withdraw assets much faster if you want to. I've been showing the mempool a couple of times, pretty much in every diagram of the architecture. But what exactly is the mempool on Starknet? So the mempool is a little bit different from what you might actually know on Ethereum, because on Starknet, we don't have a fee market yet, right? And the fact that we have a fee market, it means that transactions are executed in the order they arrive. It's not like you can pay more in gas fees to jump the queue, as you can actually do on Ethereum. Eventually, we're going to have a fee market that's coming this year. But right now, it's just the first transaction to arrive is the first transaction to be executed. So
correct me if I'm wrong,
yeah.
but I think that no layer 2 has a fee market yet.
I don't know if none of them, but most of them have the same idea that as soon as the transaction arrives, that's when finality counts. It's just because it also, if you don't have a single sequencer, also it doesn't make sense to have a real mempool to broadcast transfer them. Eventually, all layer 2s, when they decentralize, they will need to have a proper mempool, and maybe this layer 2 finality won't be 3 seconds, will be a little longer because now you have to wait for consensus on layer 2 to happen.
So could we
But
say
for now,
that,
I think probably most of them, if not all of them, they use the same approach right now.
could we say that we have a mempool then in that, like
We
an
have,
actual mempool?
but it's so basic that it's pretty much a batcher. That's the other name that you will hear it on Starknet. Basically, there's transaction and they send it to the Cairo VM to be executed. It does some basic validation of transaction, but it's super basic. I want to put the mempool there just because it's a term that most people are familiar with instead of the yeah, as I mentioned, as we get to decentralize, we're gonna need to have a real mempool because now we need to have a P2P network as well, and that is being worked on, and that is part of the roadmap to decentralize Starknet. I haven't talked about the pending block, and this is important to understand the difference between a transaction being executed and considered to be accepted on layer 2 versus block creation. Those things are not the same. So on a Starknet, the first status that a block will have is pending. And a pending block is just a block that is not yet created and it doesn't have yet all the transactions that it will hold. So when a new transaction arrives to the sequencer, basically what it does is eventually it gets sent to this pending block that is still open. And as soon as it arrives, it actually gets executed using the Cairo VM, right? And that's when you get the status accepted in L2, and you get the layer 2 finality, right, in 3 seconds. That's why it happens so fast, because the block is not yet even complete. It's still accepting new transactions. Another transaction will arrive later, and it will get added to the same pending block, and the same process repeats. That second transaction gets accepted on L2 and gets to be, it gets executed in the card VM, accepted on L2, and is considered to be final in 3 seconds. Eventually, the block will have enough transactions and it will actually be created. It's no longer the pending block, it's a created block. And that happens when the block actually reaches a certain, I think it's by time, every 3 minutes or so, a new block is created. But the maximum amount of computation that you can have on a Starknet block is 10 million carat steps. And the maximum amount of computation on a single transaction on the Starknet is 3 million carat steps, right? Carat step is like the smallest computation that you can do. Doug is asking, isn't it weird that although finality is 3 seconds, all explorers on a Starknet are quite slow, to the point it sometimes makes debugging cumbersome? Yes, because that's gonna now connect with the role of the full nodes and how they actually work. And you're gonna see some of the discrepancies there. Maybe later when you get the full nodes, you're gonna get a better picture of why this could happen. Okay, so blocks are created more or less every 3 minutes. And we can take a look, for example, we go back to StarkScan, a block explorer. We see all the blocks being created. They have blocks, yield blocks. You see the difference in time, right? It's about 3 minutes between them, about more or less. All right, back to the slides. So to see all these events in a single timeline, right? It all starts when the sequencer receives your transaction, that is, let's say, time 0. Then about 3 seconds later, the transaction gets executed in the sequencer. That is what we consider to be layer 2. 3 minutes later, and this is 3 minutes after being received by the sequencer transaction, that block is actually created, is minted. And then 2 hours is when the validity proof that corresponds to that transaction and that block is actually sent to layer 1 and verified. That's what we consider to be layer 1 finality. Just keep in mind these 3 events of the network.
But there's a question by Dogus. The validity proof is only for a single block or multiple?
Multiple blocks. And that goes back to when we talk about the Starknet OS here, you can see that it's actually waiting for multiple blocks before execute the program, and it start the whole process of proving and send it to layer 1, the validity proof. So yes, multiple blocks in a single proof. Doug is asking, what is the use case for block creating here? Right now, not much, but as soon as we decentralize the sequencer, it will be actually important because that will going to be closer to finality, similar to an Ethereum, right? Okay, to summarize transaction finality, transactions are executed in the order they arrive. New transactions arrives, it means that they get added directly to the pending block as they arrive. Transactions are executed right away, and that's we consider to be layer 2 finality, happening every 3 seconds. Layer 2 finality happens before the block is finalized or before it's technically created. A new block is created every 3 minutes, more or less. A block can hold up to 10 million carat steps, which was actually recently increased from 8 million to 10 million. And a transaction can hold up to 3 million carat steps. And that is a lot. So you can do pretty complex computations in a single transaction on a Starknet. Going back, what is the value of blocks? Actually, it's not nothing, because when we get to talk about the Starknet core smart contract, you're going to see and you're going to see how this data is actually being used by full nodes as well. So what is a full node? A full node is a way to answer questions about the Starknet state, right? About, give me details about a block, details about a transaction, and the sort. So users don't directly interact with the sequencer, only full nodes do. And that is something that we changed in the last few months, because up until recently, many tools and apps actually talk directly to the sequencer. And that is a problem because we have a single sequencer. So as you can see that it doesn't scale, right? At some point, the sequencer gets overwhelmed trying to answer all the questions from all the people and all the apps. So the idea is to, well, let's have some full nodes that actually can provide the same data to users without directly touching the sequencer all the time. So it's kind of equivalent to an execution client on Ethereum, to something like Geth or Nethermind, but for a Starknet. And we actually have 3 different clients, believe it or not: Juno, Pathfinder, and Papyrus. Juno created by Nethermind, written in Go, Pathfinder created by EQ Labs, written in Rust, and Papyrus created by Starkware. And you can find the link to all of them on GitHub. They're all open source. And you can actually run, if you have your own node, for example, I have an Ethereum on the ARM project at home, and actually I can run the Juno full node on my computer, on that computer. Full nodes also expose an RPC server. That's what you can use to actually fetch data about Starknet. And you can see the specs in this link because the RPC specs changes every so often.
There's a question by Paulo.
One block contains 3x transactions. No. One block contains, I don't know how many transactions, a lot. Like if every transaction uses the
120.
maximum amount of Cairo steps, then yes, it will be close to. But transactions don't get that big. Maybe we can take a look. I don't know if we can see that on the Block Explorer.
Last time I saw it was around 120, more or less.
Look, this has 22 transactions. It will depend on the complexity of the transaction, I guess. Let's take another one. Oh, you can see here, number of transactions per block. So it's all over the place, like 100. Yeah, you can see it here on StarkScan.
So the nodes do some kind of validation of the transactions?
No, only
they don't do any.
Not that I'm aware. Maybe they perform some basic validation, like the structure of the transaction being correct. But signature verification, all that, it happens on the sequencer. And I'm going to talk about that now. Okay has a question. Is there any benefit of an average developer running a full node? You will get to run your own RPC if you want to be independent and not depend on Infura or Alchemy. That's one benefit. But okay, so what happens when you actually want to read from Starknet? And now keep in mind that the idea is not to directly talk to the sequencer anymore. So what happens is that you will send your request, and I'm saying request because when you read from the state and not modify, it's not a transaction. It's just read the state. You will talk to a full node, right? And this full node could take the form of an Alchemy service, Infura. They both support Starknet. It could be your own node, Papyrus, Juno, Pathfinder. That goes through the RPC server in the full node. And from there, it actually talks to the state manager, which has the database, which has all the state of Starknet, and the Cairo VM as well. We have two different state managers right now, Blockifier and Starknet in Rust. So depending on the client, the full node, either Papyrus, or Juno or Pathfinder, they might actually choose one over the other. So your request to read data from Starknet actually goes to the state manager, and you will get the response right away, right? This is, for example, if you call a view only function, you get the response without never directly talking. But obviously, once in a while, the full nodes needs to talk to the sequencer to get what are the new blocks that have been created. So they get a request and update, and they talk to a module called the feeder gateway inside the sequencer. Basically, it's only used for reading. And the sequence has also its state manager, right? In this case, in particular, it has Blockifier, it doesn't have Starknet in Rust, and gives back, hey, these are the latest blocks being created since the last time you actually interacted with me. This is one of the reasons why sometimes Block Explorer takes longer to give you the updated information, even though your transactions been final on layer 2, is because they actually have to wait until blocks are created to get all the information to display it to you, right? Otherwise, we go back to the same issue of overwhelming the sequencer, just making too many queries in a row. Okay, clear? Any questions about reading? Okay, Douglas' question. Can I create the sequencer for the latest state if I don't want to wait 3 minutes? You can see the sequencer now, it has a limited amount of endpoints available these days. It's mostly to get information about blocks. So I don't know if you can I haven't looked into it, which endpoints are actually available for the feeder gateway these days. It used to be the case that you can read anything you want. These days, not. Because you're supposed to talk to the full nodes for that reason. But I don't have exactly what is available today. All right, that was reading from Starknet. What about writing to Starknet? So when you write to Starknet, you have to send a transaction, and you have to sign the transaction when you send it. And again, you send it to the full node. You don't send it directly to the sequencer. So the RPC is going to get your transaction, but the full node cannot do anything more than that, right? Because the full node cannot change the state of Starknet. It can only read and tell you what's the current state. So it will simply pass your transaction to the sequencer. In this case, to a service called the gateway. The gateway is for writing. And that's when the whole flow that I mentioned before, going to the mempool, it goes to the state manager because that's where the Cairo VM actually lives and modify the global state of the network. Going to the Starknet OS, when you have enough blocks to justify creating a validity proof, going to sharp, this is the same as before, right? Nothing new from this point on. And then the validity proof and the data availability information sent to layer one. The only thing new here is that when you send a transaction, you don't send it directly to the sequencer. You send it to the full node, and they're more likely like a proxy for you to talk to the sequencer. So the full node doesn't do much in the case of reducing the load of the sequencer when it comes to writing. It helps mostly for reducing the load when reading from Starknet. I mentioned that there was a third smart contract on layer one that I needed to mention, and that is called the Starknet core. And that is important because once we finish sending the whole thing, validity proof and DA to layer one, now there's another module in the sequencer. It's called the Starknet operator that starts to send also transactions to layer one, but in this case to register checkpoints of all the blocks being produced or all the blocks that are part of this validity proof. But it doesn't send the whole block. It just pretty much like part of the header, like the block number, the block hash, and the global root hash. And it sends that one transaction per block, and it actually gets stored on this smart contract. It's not just cold data as in the case of the memory pages. If you take a look at this smart contract on layer one, you see the update state transaction. And I think if we go deeper into the details, see, show more, you see, I saw it somewhere. Oh, it's in the logs, I believe logs. Right. You see that it creates events, global root, block number, block hash. So why is this important or how it's used? Well, Pathfinder, which is one of the layer 2 nodes available, it actually uses this information when you are syncing a layer 2 node for the first time. So the way that it works is that basically Pathfinder, when it's syncing your node, it requests a block from the sequencer. Give me a block, right? And then it calculates hash. Then it actually compare this root hash of the layer 2 block to a checkpoint of that state on layer 1. And it says, okay, if those two hashes actually match, this block is valid. And then you move on to the next block and you ask the next one for the sequencer, and you keep synchronizing your node. Otherwise, you say, okay, this block is invalid and match. So that's one way to get some certainty when you are synchronizing a full node. I don't know if all the full nodes do this, but I know for sure Pathfinder actually does it. So in summary, full node answer questions about Starknet. We have 3 implementations, Juno, Papyrus, and Pathfinder. We have 2 state managers, Blockifier and Starknet in Rust, and both the full node and the sequencer have a state manager. The sequencer in particular uses Blockifier, which is the one created by Starkware. Starknet stores block roots on Ethereum, as I mentioned on the Starknet core, and they can be used for block verification. And Starknet core is also used for sending messages between layer 1 and layer 2. Having discussed that, I don't plan to discuss that in this Basecamp because there's a limited amount of topics that I can cover, just 4 sessions. But if you're curious, go to the docs or the resources that we gave you before to learn more about how can you actually send messages between these 2 layers. And that actually goes through the Starknet core smart contract on layer 1 as well.
There's a question from Matt. What's the Starknet operator contract purpose?
It's the interface of the sequencer with layer 1. Similar to the blockchain writer. The blockchain writer is for Sharp. This one is for the sequencer.
David, are you aware of what is the architecture of other validity rollups or zero knowledge rollups? Are they similar to Starknets? Do you see critical differences?
I mean, the only one that I at some point looked at was Polygon CKEVM, because they were doing something interesting. Is that they use a start under the hood, but when they have that single proof ready to be settled on layer 1, they don't send it as a Stark proof. They actually then verify that Stark proof using the snarks, and then they send the snark proof to layer 1. So I guess that they're doing that to reduce the cost of verification, but then you lose a lot in security in the process. But Yeah, and they have their own internal they have their own VM, like kind of like a Caro VM, but their own version. Even though they're a CK EVM, it was quite interesting. I don't know if it has changed since then.
All right. So there's kind of space for innovation in there, right? Like, or at least different ways to do it.
Yeah, and many teams will, explore different ways, and I think we all learn what's working and what's not. It's beneficial, I think, for all of us. Aside from that, I haven't looked too much into fraud proof, for example, for optimistic rollups.
Will be interesting to see the crucial differences between the validity rollups or at least Starknet against an optimistic rollup. Let's see what the sequencer is being used for in optimistic rollups.
Yeah. One thing interesting from Solana, for example, is the fact that they can execute transactions in parallel, and that way they have like a different fees depending on which thread you land your transaction to, something like that. But the fact that you can run transactions in parallel is very interesting, and that is something that we're gonna re-enable on Starknet as well, with optimistic parallelization coming this year at some.
I think that was invented by Sui or Aptos, something like that, and it's been very useful, and it's something that we can do since we're not following the EVM. So that's also.
Oh, you mean the optimistic parallelization was pioneered by them?
Well, I don't remember if it was called optimistic parallelization, but it was parallelization of transactions.
Okay, interesting. I don't know. There you know. We actually. All right. Let's talk about recursive proving. For me, one of the most interesting features of Starknet. And this is basically showing you what's the difference in complexity versus executing a transaction without doing anything, like no proving, no nothing, just execute a transaction, versus the effort of validate the integrity of that transaction using a Starknet validity proof, right? So the relationship was, while the sequencer has to do X amount of work, let's say, for example, if the transaction requires 100 CPU cycles, the sequencer has to do 100 CPU cycles to execute the transactions. But to verify the associated validity proof, to have certainty of the integrity of the computation, it's only about 40, right? Because it's going to be log square of X based. And I saw it before, you can go to Wolfram Alpha and see for yourself, and then maybe modify some values, put bigger numbers, and it will show it to you here. What we haven't discussed yet is the effort to actually create the proof. And this is the effort done by Sharp, by the prover. So now, if the effort to just execute a transaction is X, the effort to generate the validity proof for that transaction or for that computation is actually X log X, right? Again, this is base 2, the logarithmic. You can see visually the difference, the blue line being the effort of the sequencer, while the yellow line will be the effort of the prover to create a validity proof. So there's a big gap between the two. So you can see why it takes a lot of effort. Even though verification is cheap, the proof creation takes a lot of effort to perform. So, there are different approaches to try to play with this gap in a way that is not too much of a burden to the. And the first, let's say, the naive version of a way to approach this will be, well, what if we have, a small carry job? Carry job is the program that you want to actually prove. That's how the sequencer, that's how Sharp names things that it needs to prove, right? Like the output of the Starknet OS for Sharp is known as a carry job. Let's say, for example, what if we take 3 transactions and create a program out of that and say, hey, prove me this program, right? Execute these 3 transactions. So because the proving is actually X log X is a lot of effort, let's say it will take this amount of time, while the verification layer 1 of this proof will be small, right? So it will be log square of X. So what if we now, bundle many more transactions into the same validity proof, and we create a proof of that? So what's going to happen is that now the amount of time and resources required by the prover to create the validity proof will increase, right? Because as you can see in the previous slide, there's a big gap in complexity of the computation between the two. So the verification will remain roughly the same. It's not going to change that much, but the proving part is going to actually increase a lot. And that is a problem, because in the first scenario, you will have faster layer 1 finality, because you basically can send the prover to layer 1 faster, but then you will have a much higher transaction cost. because the similar amount of effort to verify the proof on layer 1 is distributed to only, let's say, 3 transactions in this example, compared to the other approach will give you lower layer 1 finality, because now the prover needs to do way more work, takes more time. But the proof verification is roughly the same effort, so you get lower cost because the same cost is get distributed among many more transactions. So, as always, it is a trade-off between these two properties. But there's a way to get out of this trade-off. Before I show you how to get out of the trade-off, I just want to mention that in our diagram so far, I always show you that Sharp has a prover, single prover, but it's not really the case. We have the Sharp has many provers, right? So it has many computers inside of it doing the job of a prover. And also Sharp not only serves Starknet, not only creates validity proof for Starknet, it also serves all the StarkX apps, the DYDX, Surveyor, and others. So just when you think about Sharp, and even if I show you just a single prover, just keep in mind that it actually has many of them. And it has many of them because it's able to generate or process or create proofs in parallel and then combine them into a single proof. And that's what's called recursive proving. It's the act of creating proof in parallel with multiple provers. So let's see how it will work, at least in abstract sense. Let's say that Starknet is asking the prover, hey, please create a validity proof of this execution, right? Which is the output of the Starknet OS. Take that amount of effort. So that proof generation is happening off-chain, which is in the case is happening on Sharp in one of the many provers. But then the StarkX apps also come along and say, hey, create a proof for me for DYDX, or create a proof for Surveyor, or for Rhinify. They all come with a request to create a proof out of their executions. So now what happens is that after the proof is created, that proof is not directly sent to layer 1 for verification. It's actually sent to a verifier inside of Sharp written in Cairo. So this verifier is actually verified this proof being created here inside of Sharp. And because verification is a computation and it's done in Cairo, you can generate a proof of that verification. So what you do is basically you combine the effort, you create a new program, which is the combination of these two programs, and you prove that one, right? You're proving the verification of 2 Cairo jobs. So you have what's called a recursive proof. The same happened with those 2 other Cairo jobs from StarkX. And you can do this multiple times, right? So this recursive proof, again, you verify the proof directly on Sharp using a Cairo program, and then you combine it again in a second recursive proof. All of this happening within Sharp theorem, but eventually you're going to have a single validity proof that attests to the computation of all these 4 services, starting with the XOR and Rhinify. And you can see that that is the proof that is actually sent to Ethereum to be verified there. So you can see how we actually escape this dichotomy of the size. With recursive proof, what you actually are able to achieve is create proofs in parallel, and then you have a single layer 1 proof for many layer 2 transactions, either from Starknet or StarkX, which will give you fast layer 1 finality and low transaction cost, right? So this is the holy grail. This is why Stark's proofs are so powerful, because to my knowledge, these are the only ones that you can parallelize this way. And this is the reason why, for example, I think Polygon, under the hood, they also started to use Stark proofs for this reason as well. So my guess is that over time, many, if not all, CK layer 2s will migrate to Stark's, either just internally or even just settling directly on layer 1 as Starknet is doing. So these 2 charts that I showed before, right, for verification and for proving, I always mention that this is the baseline. And I always say that it's just because these curves actually change a lot when you take into account recursive proving, right? They get much better. In the case of verification, these lines get wider. And in the case of the proving, actually they get narrower, right? What you want for performance. So let me give you a more detailed example, having 4 different Cairo jobs. I want to say Cairo job is like one for Starknet, one for DYDX, blah, blah, blah. 4 of those. And I'm going to show you like the different ways to combine these proofs to get to the point to how actually Sharp does it. So if you recall our baseline, right? Like if the amount of work being done to execute all the transactions in that program is X, we know that proving is X log X, while verifying on Ethereum will be on Ethereum or directly in Sharp will be log square of x, right? That's the baseline. When we have 4 jobs, let's say first scenario, what if we try to execute all these things and prove them in sequence? So what you will have is now, instead of having a single x, the effort will be 4x, right? Because now you have these 4 cairo jobs that need to be proven. If you do it in sequence, now your baseline job is 4x instead of just x. The proving of these 4 cairo jobs in sequence will be 4x log x. It's basically x log x. I just replace who is x in this scenario. It's a new value. While the verification will be log square of 4x. It's going to be some math here, but just keep in mind, just replacing values, right? Nothing too fancy here. So if we were to execute this in sequence and prove them in sequence, this is what's going to happen. This is the values we get. Now, what if instead of doing in sequence, we actually combine in sets of 2? 2 cairo jobs in a proof, well, 2 cairo jobs in another proof, right? So these 2 computations are proven in parallel. So now the new baseline for the computation will be 2x. So you replace it here in the effort for proving. So now you're proving in parallel. Now you verify also in parallel directly on Sharp on layer 2. This will be the effort to verify on layer 2. Then you combine these 2 computations, these 2 verifications in a new program. And obviously it's just 2 log square of 2x, right? This is the complexity of the new program. And the proving is just basically take this number and replace x log x with this is your new x. This will be the effort for proving. And this will be the effort to verify on layer 1. This is going to make more sense when I show this in a chart instead of the numbers, but I just want to give you the gist of how I got to this. Now, the way that actually Sharp works is that you prove them all in parallel, right? The job 1, 2, 3, and 4, they all go to different provers within Sharp. So now the effort for each one of them is x, or the amount of computation. Proving is x log x for each one of them. So now we're using 4 provers within Sharp. We use 4 verifiers within Sharp to verify this proof directly on L2. We combine them, right? So now the new job will be 2 log square x. Just basically take these 2 programs and create a new program. This will be the proving. Again, these 2 happens in parallel. This verification happens on directly. And eventually, we send a single validity proof to Ethereum that attests to all this computation of these 4 cairo jobs. And this will be the effort of the verification. Right now, this is a lot of numbers. It's hard to put into context, but when you put it on a chart, it makes more sense. If I attempt to execute 4 cairo jobs in sequence with no recursion, you will follow this line. Only applying 1 level of recursion, look at how much it improves. And this is the amount of effort for proving. Sorry, for verification, right? So the verification, the more levels of recursion you do, verification gets easier and easier and easier, right? This is how you actually are able to bundle more transactions, and the cost to verify actually gets lower on average. Now, it also benefits the time it takes to create the proof on layer 1 for all these jobs. So again, if this is the time axis, if I were to execute these 4 jobs with no recursion, just in sequence, it will take like this amount of time. This is just a relative. If I apply 1 level of recursion, you can see that already I'm able to settle earlier, right? The same amount of work gets settled earlier. But if I do it directly, everything in parallel, you settle even earlier than that. Is the x-axis equal to CPO cycles? It's equal to time, but yes, it's also equal to CPO cycles. So time, and it's talking about resources, which could be time, or could be CPO cycles. So you can see that not only you gain in that you decrease the cost of verification, you actually do it faster with recursive proofs. But not only that, you can see that the machines used internally for proofs, actually they have to do less work. It means that you can use cheaper machines for proving, which now impacts the price of how much does it cost to create the proof within Sharp, because expensive machines are, more expensive. You have to pay premium for those. So this is how it looks like now, the complexity for the proof generation. This is if you had no recursion. Now, if you have 1 level of recursion, you can see how drastically it reduces, and you want this to go lower. Try to put more versions on Wolfram Alpha, but it was too much for it to handle. But I think you can see the pattern is getting down and down, right? You can follow this link and see the math yourself there. So,
Cool.
In summary, recursive proving, what you get is that Sharp, basically, first of all, it serves multiple protocols, Starknet and all the StarkX apps. It has multiple provers because you want to parallelize proving. And this is only possible because it's based on ZK Starks, which allows for parallelization. Those parallel proofs are combined using recursion, which I showed you graphically how it kind of works in abstract, which has some benefits, which you can have more operations on a single layer one proof, which reduces the average cost of those layer two transactions, reduces time to L1 finality, and reduces the proof respects. So you get three great benefits by having recursive proofs thanks to ZK Starks. And that's pretty much the last section of today. Maybe start with you, Omar. You have any question?
No, just to mention that this work that David did to uncover this and expose it is amazing. It's something that, to my knowledge, hasn't been shown. Oh, actually, all this class is something that hasn't been shown with such detail before. So congrats to David, because there's a lot of quality here and we're learning a lot. It's the first time ever that somebody exposes this, so it's amazing.
Yeah, thank you. This is basically special because made the effort to bring, much not only up to the information, but better information than last Basecamp that we had.
Yeah, also, it's David's
Paulo
birthday.
Sorry, what?
Is Sharp running as a cloud service? I think so, right?
I believe it does. I believe it runs on AWS right now. Yes.
This is very interesting, and you spend a lot of time trying to understand this, right? And trying to because you told me that there's a lot of information in the heads of the Star Wars team, but
yeah, there's something that are not captured in the docs or books. One of the goals with Basecamp is to fill the gaps for us internally at the foundation and for you developers learning this.
By the way, if somebody wants to, something that we want to do in the Starknet book is to update it with or add all this information that David has on covers. Also, the amazing slides from David, we want to put them as images there in the book. So if somebody here wants to contribute there, please open an issue or message me in Telegram. And for those that already finished, take a look at this. This is amazing and something to be very proud of. So here you can see the developer report, which is the most used report on the number of developers that all blockchains have. So if you take a look at this table, it shows the top ecosystems on active developers. It's ordered by full-time developers. And as you can see, Ethereum has more than 2,000 developers, but practically all the different ecosystems have lost a lot of developers from 1 year to now. So this is very bad for the ecosystem, right? Ethereum, Polkadot, Polygon, Cosmos, doesn't matter which one, they already losing developers, which is not okay for us because developers are the ones that, like you, that are building the crypto ecosystem, the ones that are thinking in new stuff to build. So if we lose you, then we lose a lot of innovation that we can do. But if you start going down, you can see that the Starknet, well, and then you can see also CK Sync, Moonbeam. Well, after that is red numbers. But basically, Starknet is the blockchain with the highest number of developers, almost 200 full-time developers in Starknet, and it continues growing, almost 40%. So it's the biggest network that grew during the last year. So this is amazing. It means that developers in Starknet are built differently, and this shows that. And this is amazing, and that's because of you. Thanks to Basecamp, thanks to all you the developers that are joining the army, the Starknet army. So thank you and congratulations. We're in a good place where we are growing. It doesn't matter if it's bull market or bear market. It shouldn't matter for us. We just want to build, and here it is.
Yeah, those were really impressive numbers. Like, I think Starknet has like 1,000% increase, something like that, crazy from 2020. And
yeah,
how many full-time developers?
Almost 200, 198.
This
is very cool.
There is a protocol that has to create its own ecosystem from scratch, not reusing Ethereum tooling.
That's very true. Yeah, that's very, very true. A lot of people say that Cairo is too hard, Starknet is too hard because it's not EVM compatible and so on. But to be honest, we can see that the number of developers in Cairo continues growing, and also developers in Starknet projects continues growing, and it's like a trend. This happened the last year too, and last year. So I don't know. It's amazing, and we are built different, and we love our developers.
Hopefully, some of the people in the call here today will be part of this full-time
No, I
developer for the
know, I know.
next port.
Actually, no, I know for a fact that some of here have already been counted there. For example, Dalmas, Carlos Colorado. There are several here that have already been counted there. So, and we hope you join the other ones. We hope you join the started ranks.
Thank you for coming today, and I'll see you
Thank you,
all
David.
again next week for session 3.
Thank you, David. This was amazing. And please contribute to the started book, this content that David just showed us. Thanks, David. Thanks, everybody.
Bye.